all of this component work we've been doing is heading us toward working with forces in 2 dimensions. So today we're going to start dealing with forces that have components, right? Forces that are applied at an angle. So let's go ahead and try one here. I'm going to write this problem up on the screen, and you can copy it down as we go, and we're going to start working with it. Okay? So it says, a rope is pulling a box with a force of 50 newtons at 62 degrees to the horizontal. What is the normal force of the box? We've got our system. This box is sitting on the ground and we're using a rope to pull it. Okay, so can we envision what's happening here? I've got some box sitting on the ground and I'm pulling on it like this. I'm dragging it. Okay, it's dragging on the ground. Can we envision what's happening here? But I'm pulling it with a rope at an angle. Okay? So this box is sitting on the ground. What are the forces that we already know have to be acting on this box? Gravity, always gravity. The normal, because it's still resting on the ground. It doesn't tell us anything about friction, so we can leave out friction. Okay? But we also have this force that's being applied at an angle. So we're going to go ahead and draw it at that angle. Okay? And our force we know is 50 newtons. This phrase right here, 62 degrees to the horizontal, means that this force is being applied 62 degrees above the horizontal positive axis. Okay, so here's our positive horizontal axis. Our angle fits right in there, 62 degrees to the horizontal. Does that part make sense? So whenever it says to the horizontal, we think north of east, right? We think that most simplistic angle right there. All right? So what would we call this 50 Newton force if we were going to name it? F what? Applied. You could call it F pull. You could call it really whatever you want. F rope. Anything you want to name that is fine. I'm probably just going to stick with F applied. Okay, because we know we're applying that force of the pull. Okay, so when we deal with free body diagrams and we deal with forces, we still want to deal exclusively in vertically and horizontal forces. Okay, vertical and horizontal, we want to focus on those. So we're going to break down this angled vector into its components. Okay, this force that's being applied at an angle has a vertical and a horizontal component. So we're going to break it into those components. So what would I name this side of my applied force vector triangle here? What would I name that? If it's the y component of my applied force, yeah, F applied y. Okay, it's the y component of my applied force. Okay, so what would I name this side right here? F applied x. Good. Okay, so now what essentially I have is I have an x component and a y component, and I can be done with my angle once I break those down. So let's solve now for F applied x and F applied y. Okay, we're going to find the components of that force that's being applied at an angle. Components of that force. So if I want to solve for F applied x, am I going to use sine or cosine? I'm going to use cosine because it's adjacent to that 60-degree angle. So I'll take 50 newtons, which is my hypotenuse, times cosine of 62 degrees. Make sure your calculator is in degrees. not radians. Do we agree with 23.5? Okay. If we want to solve for f applied y, we want to take 50 times sine of 62 because the f applied y is opposite of my 62-degree angle. Are both of my components heading in the positive direction? Yes, so they get to stay positive. Okay, so what essentially I've done here, I'm going to draw a second free body diagram just so we can take a look at what's happening here. We've got our force due to gravity. We've got our normal force. And essentially what we've done is we've taken F applied y and made it a vertical component. And we could add it right on top of the normal force, and we could take F applied x and keep it as a part of our free body diagram in the horizontal direction. Okay, you don't have to redraw your diagram like this, but this is showing us that now we've got all vertical and all horizontal components. We're not dealing with the angle anymore. Once we break down that angled vector, we're done with it. Okay, so 50 newtons will go nowhere in our problem after we break down that vector. So if redrawing those, sorry, this should say F applied y. If redrawing those on your free body diagram, redrawing those components so that you see only vertical and horizontal help you, that's fine. Go ahead and do that. Okay, but if you can see it without, that's great too. Okay, but now our overall goal is to find the normal force. Okay, so let's think about what's happening here again. I'm dragging this object at an angle. Is it leaving the ground at all? No, it's still sliding on the ground. So in the vertical direction, right, I'm looking for the normal force. That means I want to look only at vertical forces. In the vertical direction, does it have any acceleration? No, so that means F net in the y direction has to be 0. Right? This is not accelerating in the vertical direction, so the net vertical force has to be 0. So let's set up our net force equation. 0 equals upward forces minus downward forces. Okay, so we have how many upward forces? 2. F normal plus F applied y minus what downward force do we have? Force of gravity. Okay, so in my equation, I forgot to give you the mass of the box. I forgot to write that in there. The mass of the box is 24 kilograms. Sorry. Okay, that's going to help us a little bit. All right, we're solving for the normal force, so that gets to stay. F sub n is what we're solving for. Do we know F applied y? Yes. Yeah, because we broke that down. So 0 equals normal force plus F applied y, which we solved right here to be 44.1, minus F sub g, which is mass times gravity, 24 times 9.8. That means my final answer for my normal force is equal to 191.1 newtons. Okay, that's because I took 44.1 minus 24 times 9.8, and then I moved that to the other side to equal my normal force. So on the worksheet I handed out, this is number 3. Two horizontal forces act on an object. So here, I want you to kind of envision, it's like a tug-of-war type situation, right? There's something hanging, and we've got two horizontal forces acting. So in this particular instance, we're thinking about, we're not concerned about gravity or the normal force here because it's kind of something suspended in midair. Okay, can you imagine what I'm talking about, like a tug-of-war? Okay, so we've got two horizontal forces acting on our object. So let's go ahead and draw our free body diagram here. One is 10 newtons west, the other is 20 newtons, 30 degrees north of east. Okay, so we're going to go ahead and draw our free body diagram. 10 newtons west. And our other is 20 newtons at 30 degrees north of east. So 20 goes on our hypotenuse, and the 30 fits right in there. Okay, so do we envision what's happening here? We're not concerned about the gravitational or the normal force because it's not resting on anything. We're not real concerned about gravity here because we're just going to assume that vertically it's not moving at all. Okay? So we want to find the net force on our object. We want to find essentially what direction is this object going to start moving. If we're pulling at it in opposite directions, it's going to start moving somewhere. Right? That's what happens in a tug of war, is that when we pull at objects from opposite sides, it's going to start moving in that direction. Okay, so we want to find out where it's going to be our overall path on this object. Where is it going to start moving to? Okay, so let's look first at the x direction. We need to find, let's label these sides first. We can call them really whatever we want. If we want to say that 10 newtons is F sub 1 and 20 newtons is F sub 2, what would we call this side? F sub 2y, good, and F sub 2x. Okay, force 1 and force 2. So overall net force on the object, that means we're going to find the net horizontal force, we're going to find the net vertical force, and then we're going to build our new resultant triangle to find our overall net. Okay, our overall resultant force. So let's do x direction first. Let's do x direction first. So if we're looking at F sub 1x, what's F sub 1x equal to? Negative 10, right? Because it's going west. What about F sub 1y? Do we have any y component to our first force? No. F sub 2x and F sub 2y, we're going to have to do a little work to find those. Okay, because it is a component. So F sub 2x, do we use sine or cosine? Cosine. We use cosine because it is adjacent to that 30-degree angle. So we're going to take 20 times cosine of 30 degrees. Make sure that you're plugging these things into your calculator. Don't just follow along with my math. I want you to be able to see and feel those numbers come out so you know you're doing it correctly. You get into a habit of doing that. For F sub 2y, we'll take our hypotenuse times sine of 30. For F sub 2y, do we have any negative components? F sub 2, I'm sorry, F sub 2, are either x or y negative? No, they're both going in the positive direction. Okay, so now we can start looking at our overall net force in the horizontal direction. Okay, so if we want to look at F sub x, or our overall net force in the horizontal direction, we still take rightward forces minus leftward forces. Okay, so what's our rightward force here in the horizontal direction? 17.32, right? It's F sub 2x. This is our rightward force. This is our leftward force. So we take 17.32 plus negative 10. Okay, or you could just minus 10. That's fine. Which gives you 7.32 in the positive direction. If we look at our overall net force in the vertical direction, how many vertical forces do we have acting? Just one. Okay, and it's F sub 2y. We already know F sub 1y is 0. F sub 2y is 10. So it's going to give us 10 newtons in the positive direction. Okay, so now we've got our x component here, and we've got our y component of our overall net force. And we're going to build our new triangle. Okay, I know they both go in the positive direction because both my components came out positive. I ended up with positive 7.32, which means my horizontal component needs to go east. I ended up with positive 10, which means my vertical component needs to go north. And my overall net, I'm going to find by finding the hypotenuse of that. How do I go about finding this angle right here? Second tangent. Remember, second tangent or tangent -1 of opposite over adjacent. So 10 divided by 7.32. And our angle is blank of blank. What is it? North of east. Perfect. Okay, so what this is telling us is that in this like tug of war situation, we've got two people pulling, and our overall direction of our object in the final seconds or whatever after it's this tug of war, it's going to end up going somewhere in this direction. Okay, here we started with a 30-degree angle. We're ending with a 50-something degree angle, 54-degree angle, and it's going to start going in that direction. Okay. So this is number 4 on the worksheet. We're going to stick here with just the forces that are given. So it says this person's in a canoe. We understand that gravity is acting, but we're not concerned about that in this particular example. Okay. This example might be easier for you if you draw them as two separate vectors. If this diagram is confusing you, you can draw them as two separate vectors, or if you want to keep them on one diagram, that's fine also. But since they're both kind of heading in the same direction generally, it might be easier if you draw them as two separate vectors. That's up to you. Okay, so I have mine drawn as two separate, just so we can kind of look at them individually here. So our overall goal here is not to find the net force, but to find the net horizontal force. So they're letting us take out that whole step at the end where we find our triangle and find our hypotenuse. We just want to find the net horizontal force. That's it. Okay, which means we're only concerned with which components, the horizontal or the vertical. We're only concerned with the horizontal components, right? We don't even need to worry about the vertical. Okay, so let's look at our first force here, F sub 1. This one we'll call F sub 2. F sub 1x is equal to what? 200, right? That's our whole force here, is only in the x direction. And it's in the positive x direction, so we can work with that. F sub 2x, do we know what F sub 2x is? 70.7. Okay, so we solved for that already. So F sub 2x, we're going to solve for that by taking 100 times cosine of 45. And we get a value of 70.7 newtons. Okay, and it's heading east, so it gets to stay positive. So now if we want to find the net horizontal force, we're going to take F net in the x direction, and we're going to add together all of our rightward forces, which F sub 1x is headed to the right, and F sub 2x is headed to the right. Do we have any leftward forces? No. So you can put a -0 there if you want. You don't have to. But if that helps you know that you accounted for it, then great. Okay, so that's our net force in the horizontal direction. That's all that we were asked for. Net force in the horizontal direction. Okay, so try this one on your own. You're going to do 3 individual forces here and solve for the components, and you want to find the overall net horizontal force acting. Okay, you don't have to ignore what part A says. I want you to find the net horizontal force.